Hey everyone, welcome to podcast number 15, where we are going to dive into strong acid, strong base titrations. So the rest of our podcasts in this chapter are going to deal with different types of titrations and titration problems. All right, when we're talking about acid-base titrations, right, we probably did a few basic acid-base titrations in Chem 1, where we thought about them as neutralizing each other. And so you probably have, maybe even if you did an in-person lab in Chem 1, have done, acetic acid with sodium hydroxide as a titration and did the little titration until you saw the pink color change, the pink endpoint of that. And so we can have three different types of titrations. The first ones that we're going to focus on are our strong acid, strong base titrations. Then we're going to move on to weak acid, strong acid, weak base as we go on to other podcasts. But this one's strong and strong together. Let's take a look at a titration curve of a strong acid, strong base titration. All right, now this also works for a strong base, strong acid titration. I'm calling it strong acid, strong base because we are starting with a strong acid, because we are starting at a very low pH. So depending on where our curve begins will help us determine what we're actually titrating. That would be the thing that would be like in our Erlenmeyer flask of our titration. Remember that our strong acids ionize 100% and our strong bases ionize 100%, and they love to come together, right, and have a neutralization reaction to form liquid water. All right, well, so we have this reaction, and really this is a little bit of an equilibria reaction. Notice that this is the opposite, right, or the reverse of Kw. So the K for this reaction would be 1 over Kw, which is 1 times 10 to the 14th. That's a really big number. Right? That means that this equation basically goes to completion. Yes, there is some equilibria there, but it basically goes to completion. All right, notice that at the equivalence point, all right, we are going to have a pH of 7. All right, and so equivalence point. All right, we need to define that, and that is where the number of moles of my acid are equal to the number of moles of our base. All right, and so when I have equal numbers of strong acid and strong base, they will react together in a 1-to-1 ratio and form water, which is neutral, and so it's going to have a pH of 7. Well, here we can kind of talk about what we saw on our titration curve of a strong acid, strong base. Because we started with a strong acid, the pH starts out very low, and the pH can be calculated by doing the negative log of our H plus concentration, and this is related to the concentration of the strong acid, right? If it was like, 0.1 molar HCl, well, the H plus concentration would be 0.1 molar, right? Then we have a gradual rise in the pH, which you could see by that curve. And the pH, if we want to calculate this, is difficult to calculate. Not impossible, but it's hard to calculate that. And then as we reach that equivalence point, notice that we have that sharp rise through the equivalence point. Right? It goes up and down very quickly through that. All right. Notice that, right, at the equivalence point for strong acid, strong base, this only works with strong acid, strong base, the pH is equal to 7. All right, after we got through the equivalence point, notice that the curve kept going up, and then it starts to level off as it goes up and to the higher and higher pHs. And as we stated on the previous slide, right, the K for this reaction is 1 times 10 to the 14th. Well, let's do a sample problem here of a strong acid, strong base titration. All right, and so we have some sodium hydroxide, and it requires 35 mils of 0.128 molar HClO4 out there. So we have a strong base and a strong acid. All right, number one, it asks, what is the volume of the NaOH solution? All right, so as it says in number one, right, this is a strong acid, strong base reaction, titration. And so what we want to do is we're going to find the moles of H plus that we added, and that'll give us the moles of our OH that were present. All right, because at the equivalence point, the number of moles of our acid are going to equal the number of moles of our base. That is the definition of our equivalence point. So I can find the number of moles of our acid, which are 0.035 liters times 0.128 moles per liter. And we're going to end up with 4.48 times 10 to the minus third moles. All right, now if this were a diatomic strong acid, I would have to multiply that by 2, but it's a monoprotic strong acid. It has 1 proton, so I could have said 1 mole of H plus per 1 mole of the HClO4 to get that answer there. All right, so this means that the number of moles of OH are equal to 4.48 times 10 to the minus third as well. All right, number 2, step 2 says now we have those moles of OH. We want to determine the volume of our solution. All right, well, we can use, right, the molarity as a conversion factor like we have done before. Right, I can take, right, the number of moles of OH divided by the molarity of OH, and this would equal the volume. So could we find the molarity of our OH? Well, sure we could. We were given the pH. All right, so the pH is equal to 13.68. So our H plus concentration is going to be equal to 10 to the minus 13.68, which is 2.1 times 10 to the minus 14th. All right, so then our OH concentration is Kw over our H plus. So our Kw is still 1 times 10 to the minus 14th. And again, we're going to assume we're at 25 degrees Celsius, divided by 2.1 times 10 to the minus 14th. And we get 0.48 molar. All right, now I can plug in to find the volume. All right, our volume is the number of moles of OH, which we found in number 1, 4.48 times 10 to the minus third moles, divided by our molarity, which was from part 2, 0.48 moles per liter, and we get 9.3 times 10 to the minus third liters, which is the same thing as 9.3 milliliters. All right, I wrote out the milliliters just in case we need that later, but usually we stick with our liters there. All right, let's see what else we're going to work in this problem. All right, part B asks, what is the pH at the equivalence point? And it says see figure 14.5. So C, the strong acid, strong base titration curve. All right, that was a couple of slides ago. All right, anytime you have a strong acid and strong base, then the pH is going to be 7 at the equivalence point. Again, this only works for strong acids and strong bases, and we'll see why a little bit later on, but it only works for that. All right, part C wants us to calculate the sodium cation and the chlorate anion at the equivalence point. All right, so what we're really doing here is we're finding, all right, we need the number of moles of Na, and which is going to equal the number of moles of our chlorate, right? And the reason for that is because everything is 1 to 1 to 1, all right, which is also thus equal to the number of moles of either acid or base, and we already found that to be 4.48 times 10 to the minus third moles. All right, well, if I want a molarity of these things, then we also need the total volume at the equivalence point. All right, so what you have to think is we started with 35 milliliters, and we added in that 9.3 milliliters, right, that we found on the previous slide. And so we now in our beaker have a total volume of 44.3 milliliters, which is 0.0443 liters. All right, and so if we want to then calculate the molarity, all right, then we're going to do moles over volume. We have our 4.48 times 10 to the minus third moles divided by our volume, which is 0.0443 liters. And when we calculate that out, we're going to get a molarity of 0.101 molar. All right, so that kind of ends the strong acid, strong base titration problems, right? And usually those are the easiest ones to calculate. Now we're going to turn our attention over to strong acid and weak base titrations.